We will continue our discussion of thermodynamic factors that impact the vertical growth of moist convection by discussing how static stability impacts convection. Recall from the previous modules that several processes can support or inhibit deep convection. Sufficient moisture is of paramount importance. It is generally difficult for tropical convection to become deep if the environment is insufficiently moist. However, sufficient moisture is insufficient alone to produce deep convection. It is also important to consider processes that affect the 5 factors listed at the top of this slide. For example, while low-level convergence can dynamically force convection, it can also cause moisture convergence, which helps to satisfy the moisture requirement for deep convection. Sea surface temperature and near-surface wind impact surface fluxes, as we will see in the next module. Adiabatically driven vertical motions affect static stability. Even moist convection itself is important for development of subsequent convection. The primary moisture source to the middle troposphere is convection. So in some sense, to get widespread moist convection in the tropics, you first need convection. This seems like a contradiction. However, in later modules, we'll explain why this is sometimes the case. For now, we will focus on static stability, an expression for which is shown here. The static stability parameter, which is S sub p, in the thermodynamic equation is proportional to the difference between the dry adiabatic lapse rate, which is close to 9.8 Kelvin per kilometer, and the environmental lapse rate, which varies in time and space. We've defined S sub p to be generally positive, so that when the environmental lapse rate is less than dry adiabatic, positive S sub p corresponds with upward motion and warming by condensation. The difference in lapse rate can also be expressed as proportional to the vertical gradient in potential temperature. Essentially, cloudy air rising moist adiabatically out of the boundary layer will experience more positive buoyancy, or less negative buoyancy, as the environmental temperature decreases. An increased lapse rate means that the temperature in the environment cools more quickly with height. Finally, S sub p can also be defined as proportional to the negative vertical gradient in pressure coordinates of dry static energy. Dry static energy in the tropics generally increases with height. And the definition of dry static energy is shown right here. S is Cp times T plus phi. Let's consider an example of a sounding we might see in the tropics. In the next module, we will review with more detail how to interpret soundings, or in a couple of modules. This sounding is conditionally unstable, but is nearly moist neutral, a rather common situation over tropical oceans where the sea surface temperature is high, such as in the Indian Ocean, West Pacific, or adjacent seas. The red line is another example of a conditionally unstable sounding. However, it is more statically unstable because the temperature decreases faster with height. Note that we aren't yet considering moisture in our sounding at all. Finally, suppose a parcel rises out of the boundary layer. A typical LCL, or lifting condensation level, over the West Pacific is about 950 millibars. And above that, the parcel rises moist adiabatically along the black line, which starts near the surface with a similar temperature as the red and the blue lines. The difference between the black line and the other two lines describes the instability. As you can see, the black line is much further away from the red line than it is from the blue line, so the parcel will tend to be more buoyant in an environment that has a vertical temperature structure resembling the red line. This is related to the concept of convective available potential energy, or CAPE, which we will discuss more in a different module. Eventually, we will combine the effects of moisture and temperature into a single stability metric that is based on equivalent potential temperature instead of T or theta. But the main takeaway here is that cooling the middle troposphere, say between 850 and 500 millibars, more than the boundary layer promotes the vertical growth of shallow convection. The effect of static stability on convective updraft intensity can be seen in this figure, which shows the flash density of lightning globally. Note how the majority of lightning occurs over continents. A few lightning hotspots are over Central Africa, the Amazon, and plains of southern South America, and basically any large land masses in the deep tropics, such as islands in Indonesia, the maritime continent. In contrast, oceans experience relatively fewer lightning flashes. To first order, the reason for this involves a typical static stability profile over tropical land masses versus the ocean. Over the ocean, in places where the ocean is warm enough to support widespread deep convection, the environmental temperature profile often sits near a moist adiabat. Over land, the lapse rate tends to be steeper, meaning that the temperature decreases more quickly with height. The consequence of this is that updrafts over oceans tend to be weaker than those over land, and therefore less likely to produce lightning. Nonetheless, we'll see that some of the largest annual average rainfall totals on Earth occur over the ocean. Surface fluxes, which we discussed in the next module, are responsible for this.